We've seen how we can use the pencil test to translate position versus time graphs into velocity versus time graphs. That gives us two tools to use for representing constant acceleration particle model of motion. In this video, we'll add to our toolbox by using a graphical representation that we haven't paid attention to before, and that is the acceleration versus time graph. One thing to keep in mind when translating from velocity versus time to acceleration versus time is that the slope of velocity versus time is acceleration. So how do we translate? One thing that makes our job easy is that for constant acceleration particle model of motion, velocity versus time is always a straight line, and the slope of the straight line is always going to be constant. So the acceleration versus time graph will always be a horizontal line. This makes our choices limited. The slope of a straight line can only be positive, negative, or zero. In this example, the slope of velocity versus time is positive, and it's constant. Therefore, the acceleration versus time graph will be a horizontal line that is above the zero line. In this example, the slope of velocity versus time is negative and constant. Therefore, the acceleration versus time graph will be a horizontal line that's below the acceleration equals zero line. Let's get a good feel for this by doing some practice using something called a stacked kinematics graph. We'll start out with a position versus time graph and use the pencil test to translate into a velocity versus time graph. Then we'll examine the slope of the velocity versus time graph to translate into an acceleration versus time graph. We'll put all the possible motions that could be represented by constant acceleration particle model into this exercise. In this motion, the pencil test would show us that the velocity starts at zero. That pencil would be pointing in the upward direction, and its slope would be becoming more steep as time goes on. This means the velocity versus time graph would start at zero and diverge from the velocity equals zero line throughout this segment of motion. Because the slope of the velocity versus time graph is positive and it's constant, the acceleration is a horizontal line above the acceleration equals zero line. This next segment of motion represents a constant velocity because the position versus time line is straight. The constant slope of this line is positive, so the velocity is represented by a horizontal line above the velocity equals zero line. Because the velocity versus time graph shows a horizontal line, its slope is zero, so the acceleration is zero during this segment. In this next segment, the object is still moving forward because the pencil test shows a positive slope on the position versus time graph. However, the steepness of that slope is decreasing until it reaches zero at the end of the motion. So the velocity versus time graph shows a positive velocity that gradually becomes smaller and smaller until it reaches zero at the end of this segment. Because the slope of this velocity versus time segment is negative and it's constant, the acceleration is modeled by a horizontal line that's below the acceleration equals zero line. Here are all the rest of the motions. Pause the video and see if you can predict the velocity versus time graph for the rest. In the next segment, the pencil test would show that the velocity is zero at first, then it becomes negative with increasing steepness. This means the object is going backwards, so the velocity must always be below the v equals zero line. Because the steepness is increasing, the object is speeding up, so the velocity must be getting farther away from the v equals zero line. In the next segment, the velocity is constant and negative because the slope of the position versus time line is constant and negative. Therefore, the velocity versus time graph is a horizontal line that's below the v equals zero line. In the final segment, the object is still going backwards because the pencil test shows a negative slope on the position versus time graph. But the steepness of that slope is decreasing until it reaches zero at the end of the motion. This means that the velocity versus time graph goes from a high negative value to zero as we reach the end of the graph. Pause the video again and see if you can predict the acceleration versus time graph for the rest of the segments. We can see two places where the velocity versus time graph is horizontal. It's the second to the last segment and the segment right in the middle. So at those two spots, the acceleration versus time graph should show a zero acceleration. This is because the velocity is not changing. The very final segment of the graph shows a positive slope, so that means the acceleration in that segment is positive and constant. So it's a line that's horizontal above the acceleration equals zero line. The one remaining segment, the third from the last, shows a negative slope of the velocity versus time graph. So the acceleration during that segment is negative and constant. So that's a horizontal line below the acceleration equals zero line. These exercises should give you practice translating between position, velocity, and acceleration versus time graphs. This is a valuable skill that can help you to jump between tools when modeling motion that may or may not include constant acceleration.